So we are looking at two quantitative variables, linear regression. And a reminder, linear regression means we're trying to take a line and fit it to a set of points that sort of kind of line up. So let's look at another example, this time in a spreadsheet. So here I have the year and an estimate of the carbon, CO2 in the atmosphere. This data is in our textbook. It's in StatKey. I put it into a spreadsheet. And the CO2 in this case means atmospheric CO2 in parts per million, ppm. And we have the years 1960 to 2010, and here's the original source if you wanted to look it up. These points kind of sort of line up, right? There's a slight curve to them, but they're reasonably straight. I calculated a correlation coefficient down here of 0.993, pretty high. The highest we can get is 1. So there's a strong correlation and association between the variables. Now, it looks more curved than linear, but we're just going to go with a straight line. So how do you find the slope and the y-intercept and the correlation coefficient on a spreadsheet? So on a spreadsheet, to get R, correlation, C-O-R-R, if you start typing that, you'll see the only option is correl, which is short for correlation, which is what we want. And generally, when we're playing with two quantitative variables, the functions want the y data and then the x data. So highlight your y's, comma, highlight your x's. So there's the correlation coefficient. Slope, M, command is called slope, pretty straightforward. And we're doing linear regression. And again, it says y first, comma, x second. Parentheses. So there's my slope. And then the y-intercept, B, pretty straightforward. The command is intercept. So start typing intercept of a linear regression. Enter. Y values first, x values second. So now we have the slope and the y-intercept, which gives me the equation for that line right there. And we'll do this in a couple of different ways, but let's write it down and see what it tells us. Just get a page here. Screenshot that. All right, so the equation here, in this case, the year, that's my x. Notice it's on the x-axis down here. And y is the CO2. It's this axis right here. When I use a computer to calculate an equation for a line that passes through the points, but the points don't perfectly line up, the equation is always called y hat. It's called a linear model. So I'm modeling this idea. Given a year, I'm coming up with an equation to make a prediction about some predictions in a minute, about prediction about the CO2 in the atmosphere in a given year. So my slope to 3 decimal places should be good enough here. 1.471x, and the y-intercept is negative, so I would then go negative 2571, and I'm not going to worry about the decimal. 2,571 versus 2,571.2. The 0.2 is pretty negligible. So I think that's good enough for this model right here. Slope, what does the slope mean? So to interpret the slope, I usually just remind myself that slope is rise over run. And then I ask myself, well, what's rising here? Okay, well, that's here. It's at the CO2. So the rise means a change in CO2. The run is just a year, so the run is a change in the year. And the reason I'm writing this down in detail like this is I need this information right here to write a sentence about what the slope means. More specifically, what do I mean change in CO2? Well, that would be parts per million of atmospheric CO2 from the data description. So we've got to have a data description. We've got to know how these numbers are measured. Here's pretty straightforward. So interpreting the slope here. So let's see, our slope is 1.471. It's not initially a fraction, so then I write it over 1. So this means an increase of 1 year, right, because years are on the bottom. And this is positive, so that's an increase of CO2 in parts per million. So I gotta get that into a sentence. And usually we start with the explanatory variable, that's down here, versus the response variable. So we think looking at the year affects what the CO2 will be, right? We look at a different year, we'll get a new CO2. It looks like as the years increase, the CO2 increases too, right? That's the association. That association is measured by our correlation coefficient. So it's almost 1, pretty darn high, very strong correlation. All right, so starting with the denominator, something like for each additional year, additional is my positive. Never use the word negative. If there's a negative number going on, we would say decrease. For positive, we say increase or addition. So for each additional year, the atmospheric CO2 seems to increase by 1.471 parts per million. And then since this is related to a whole bunch of different points, we usually put on average. So that's what the slope means. What's the y-intercept mean here? Y-intercept, remember, is a point. X is always 0. And so it's the point 0, whatever b is. So for us, it's 0, negative 2,571. Okay, so let's see. So this would be the year, and this would be the CO2. Okay, so 2 problems here. One is, how can we have negative CO2? Either there's CO2 in the atmosphere or there's not. So this is like, what? Other thing is year 0. What does year 0 mean? Well, here I have 1960, 1965, and so on. Year 0 would be like 2,000 years ago, between AD and BC. Really? Year 0? Okay, which one way? 2,000 years ago. Negative CO2. Not even no, right? Less than 0. Okay, so this is like a super meaningless y-intercept, but we need it to put the line in the right spot. Otherwise, we won't get the right values when we try to do a prediction. If I do a prediction, what I mean is the line doesn't hit exactly in 1980, but I could plug 1980 in here and see what I get for a value. So let's go back to the spreadsheet and check that for fun. So I'm going to put a new column here for y hat. And then let's go down to 1980. So what I'm going to do is I'm going to use my slope and my y-intercept, like plug it into the equation to calculate what the line says the CO2 would be. So equals, and my slope is right here. So let me just click on it, times 1980, click on it, plus the y-intercept. We need that y-intercept to adjust. And I don't want to autofill, please. Okay, so this says, according to the equation, there should be about 341 parts per million CO2 in the atmosphere. The actual number measured was 338.68. Notice they're pretty close together. And you can see here that the line is just a little bit above there. So here's my prediction. That's what y hat does versus the actual data. We'll talk more about predictions and actual data later. But I need that y-intercept. I can't just throw it out because it interprets ridiculously. If I don't have it, I don't get the right amount of CO2, right? If we just, in this equation here, said, forget about that stupid y-intercept, right? Then we get 2,900 parts per million, which is totally not correct. We need that y-intercept to adjust the values to be in the right range. So it is an important number. It just has a crappy interpretation this time. Slope always has a meaningful interpretation if there really is a relationship between the two variables.